Two advanced space probes are now orbiting the Sun, one from NASA, the other from Europe. They have begun studying our star up close, imaging the mechanisms of hot plasma and magnetic fields, even diving into its atmosphere, discovering new insights into the solar winds and the science of the stars. This is the Royal Observatory of Belgium in Brussels. Scientists have been studying the Sun from here for over 100 years, using telescopes like this. The observatory is also the World Data Center for the Sunspot Index. It is now receiving data from the European Solar Orbiter, a wealth of information studying the Sun up close, well within the orbit of the planet Mercury. The imagery alone is spectacular, giving us a whole new perspective of our Sun and the nearest star.
It sometimes happens, I get into my office, I download the latest data and I stare for hours at it. It's so addictive actually. Nobody has ever seen the details of the corona in that much detail before. So every time we get an image down, it's the first time we see something at that scale, and that's really fascinating. It's really discovery space that we're entering.
I was personally blown away by the quality and degree of detail in these images. And clearly, as solar physicists, we've been looking at images of the Sun for many years. But by going 3 times closer, we can get the spatial resolution up by a factor of 3. And we see things that we haven't seen before. And that's, of course, the beauty of science, to explore the unexplored.
The journey of Solar Orbiter began in 2020 and has traveled over 2.5 billion kilometers, with gravity assists from Venus and Earth.
The spacecraft is performing very well, and we are very happy about that, because it is the first time that it had to go so close to the Sun, and so in this very challenging environment. And of course the spacecraft is designed for it, but this design is all based on modeling, on predictions, so you only really know that it's going to work until you have seen it working.
Solar Orbiter is basically a research mission, but ultimately we want to be able to predict space weather. These are energetic events that could have an impact on high-tech installations on Earth, GPS satellites, power grids. And we want to make sure that in the future we can predict geomagnetic storms based on solar activity. And for that we really need to take the Sun's temperature and measure the solar wind and connect the two. By going close to the Sun, we try to capture the physics of space weather events, and we want to film on the Sun the events that give rise to changes in the near-Earth environment. And we need to fly close to the Sun to be able to measure the solar wind while it's still in a pristine, undisturbed state.
One of the great mysteries of the Sun is the difference in temperature from its surface to its atmosphere, where it increases by 1 million degrees in a process that is not yet understood. Generation of the high-speed solar winds emanating from the star is another process under scrutiny.
For the mission, it's important in many ways, because on one hand, of course, the closer you go, the better resolution you get and the more details you can see. And it's also important because we want to understand the influence of the sun on planets, on the Earth. And for that, we want to come closer and we want to see what's happening and at the same time feel around the spacecraft how the environment is changing.
So the EUI, so the Extreme Ultraviolet Imager, sees the hot corona, so to speak, the atmosphere of the sun at extremely high resolution, much higher than what we had before. And one of the problems that we are after is to understand why the corona is so hot. It's like 1,000,000 degrees or so, while the surface of the sun is 5,000, something like this. And that's really puzzling, and we're after that since decades. And we think that it's possibly because of tiny, tiny, tiny eruptions that go on all the time, but that are small, too small to be seen by other instruments. And now that with Orbiter we get so close to the sun, we can finally see them. And we did see a lot of them in the first images that we took. And the closer we get, the more we see. So we are really excited about this because we may finally be on the solution to that decade-long problem.
These measurements that the spacecraft is taken now and also later will be important to improve our understanding of the sun. One of the things we want to understand better is how the sun affects the Earth, but for that you have to really understand how the activity of the sun is caused, how it evolves, and when, for example, such a cloud of solar material leaves the sun, how it also propagates through space and goes towards the Earth. So for that we want to do several of those close passages to the sun to observe it from close by, and we also want to change the orbit of the spacecraft so that it can see the solar poles, because we have never ever seen those before, and they are important to understand the magnetic field of the sun.
The Solar Orbiter carries 10 instruments on board. Imagers of various frequency, including an X-ray spectrometer and extreme ultraviolet imager, a magnetometer energetic particle detector, and a solar wind analyzer suite. It also carries a radio and plasma wave suite, which measures electric and magnetic fields around the spacecraft.
So now the whole payload is working together. It's actually a lot of work to coordinate all that. But what that gives us is that we get a comprehensive diagnostics of the solar plasma, of the solar atmosphere. So we can, with EUI, get the dynamics, the fine scale structure, but then with other instruments like SPICE, we can get measurements of the temperature, of the density, these kind of things. So with all the instruments together, we get a comprehensive view and understanding of the physics. And then you have all the in situ instruments also that we are working with that will help us understand what the coronal mass ejections are and how they influence the physics of the heliosphere, which is the surroundings of the sun, so to speak.
By having all 10 instruments on Solar Orbiter operate together, we can really harness the entire power of this mission, which is designed to connect remote sensing observations of the sun, meaning pictures and spectra, and what you measure, essentially feeling the solar wind as it flies past the spacecraft. And for that we need all 10 instruments, and they've now all been tested and exercised and tuned like musical instruments. And so this is the first time we actually got all 10 working together as a team.
So this Solar Orbiter and the instruments on it, it's a new machine that we are bringing to a place in the space that has never been visited before. So when we do that, we cannot expect everything to work as it is designed or is expected. There is a steep learning curve to learn to operate the thing, and that's what we call commissioning phase. And we're now at the end of that phase, and we have learned how to operate our machine to the best of its capacities, and the results are actually fabulous.
it's important to have all the instruments working and operating in a coordinated way. Because one of the main goals of the mission is to link the sun and its activity with the environment. And not only the environment close by, but also the planets. And for that we want to look at the sun's activity, at the solar activity, with many different telescopes that look at it in different wavelengths. So that means they are looking at different layers in the atmosphere, and they can also measure things like the magnetic field on the sun. And then at the same time, we also have instruments at the outside of the spacecraft that will sense and measure what's happening around the spacecraft itself. So whenever there is solar activity, we can feel the effects close to the spacecraft.
Among the things that we now see for the first time are really tiny sources of energy release in the corona. And we are now very curious to find out in what sense they are connected to the large-scale structure of the solar wind and the energy that gets essentially put into the flow of particles towards Earth. And we try to really use models to connect what we see on the surface to what we see in the wind. And that is something that clearly takes more time and investigation to really pinpoint where a solar wind package came from. But we believe that we've done quite well in terms of pointing at the right place, and thereby we hope to get this complete picture of cause and effect. Close approach of solar orbiter to the sun, to about a third of the distance between sun and Earth, is so important because it allows us to get measurements of the solar wind in an almost pristine state before it gets mixed on its way to Earth. And more importantly, to combine these measurements with pictures of the sun and spectra that we can then connect and get a complete picture of the sun and solar wind.
Scientists are also studying the dangerous solar storms that affect Earth.
This first perihelion was clearly our first scientific milestone after getting all the instruments calibrated. So this really gives us good confidence that we'll be able to do this again, and we'll do it roughly twice a year when we fly by the sun again. In between, we'll be far away from Earth, so that takes a lot of time to get the data downloaded. But in between these far away periods, we have also close by periods where we can dump all the data that we've accumulated, and then it's Christmas for the scientists to look at the data and get new scientific insights.
The Parker Solar Probe is the second spacecraft now operating close to the Sun. It was launched by NASA in 2018 and has taken 4 years and several gravity assists to reach its operational orbit. Its elliptical orbit bringing it closer and closer to the star's corona, a boundary layer not clearly understood. This project has been over 50 years in the making.
The fact that the sun is hot has been a major technological challenge, and why it's taken us so long to fly Parker Solar Probe.
That design of the heat shield, where the front of the heat shield that faces the sun is hot enough to melt aluminum, but the backside, where the spacecraft electronics and instruments are, is actually at room temperature. That's been the key to getting this mission done.
This is a dream come true. One of the major goals for the Parker Solar Probe mission is to fly through the solar corona, and we are doing that now.
The edge of the Sun's atmosphere is known as the Alphen critical surface, a postulated zone where the solar wind goes from a slow to extremely fast speed, spreading out through the solar system. The Parker Solar Probe has passed through this barrier into the corona, showing that the boundary is indeed lumpy, and has sampled material still bound to the Sun.
of the most challenging scientific mysteries in astrophysics occur in a region that we call solar corona.
The instruments on board have shown that outside the boundary, the solar winds accelerate away from the sun at high speed, unable to fall back onto the surface. However, inside the boundary, the magnetic field is much stronger, and solar material is much slower, tied to the surface.
That we've always known that the atmosphere of the sun, the corona, spins with the sun, spins at the same speed that the sun does. But out at the Earth, the solar wind is moving straight out from the sun, so it's no longer spinning. Where that transition happens is very important for understanding, because that spinning of the corona actually helps slow down the sun. All stars get slower in their spinning as they get older. Parker Solar Probe sees that transition from spinning to straight happens further from the sun than we thought. And that actually has implications for every star in the universe and how they slow down. And that's important actually for the habitability of solar systems around distant stars.
Gaining knowledge of our sun will help us understand all the other stars around us. This will help us with the search for habitable exoplanets. Understanding the processes of the solar winds and energetic particles will assist with finding worlds that, like the Earth, have magnetic shielding to help protect living organisms on the planet's surface.
Parker Solar Probe is the first mission to get close enough to the sun to see where the action is actually happening, where the solar wind is accelerated, where the corona is getting heated. And we've seen a lot of new science that we don't completely understand, but there have been some remarkable results about small events that we can see in Parker Solar Probe that get smeared out in the 93 million miles between the Earth and the sun.
We are so excited for these new results coming down from Parker Solar Probe. Parker has gone closer to the sun than we've ever gone before. It's inside the orbit of Mercury. We're seeing the solar atmosphere as it emits its material out into the solar system. We call that the solar wind. And we're seeing this process up close and personal at a higher detail and complexity than we've ever seen before. Actually, as it's being formed. So we're able to study the solar wind and all of its variability and complexity up close like we just can't do from Earth.
The protective magnetic field surrounding Earth is constantly buffered by solar winds and energetic particles. At the poles, these solar disturbances create spectacular auroras. It may also cause the atmosphere to leak out into space.
So the sun not only has this constant solar wind that blows out in all directions, it has solar storms, solar flares, and coronal mass ejections. And those energetic storms can accelerate particles up to almost the speed of light. And those energetic particles can actually cause radiation sickness in astronauts if they're out unprotected when those happen. On the Earth, we're protected by the Earth's magnetic field and the atmosphere of the Earth. But once you're out in space, away from the Earth's magnetic field, those can be a danger to not only astronauts, but also spacecraft.
The sun is capable of energizing pieces of atoms up to really high speeds and energies, and these are damaging to astronauts and to electronics. Now, we're protected down here on Earth from these particles, but on the moon or beyond, astronauts wouldn't have that luxury. So one of the key missions of Parker Solar Probe is to understand how these particles are actually being accelerated so that we can better predict and protect against them.
Another phenomenon of our sun deals with space dust and debris, pieces that clump together by static electricity, and then as they grow by gravity, there appears to be none close to the sun.
Space dust is pieces of comets and asteroid debris that fills our solar system, but close to the sun, they can be so hot that they actually vaporize, or that material can also be pushed away by the radiation of the sun. And so there ought to be a region around the sun where there is no dust. And for the first time, Parker Solar Probe is seeing evidence of this dust-free zone.
So the sun goes from a quiet period, what we call solar minimum to solar maximum, and back again about every 11 years. And we launched into a very quiet solar minimum. That's actually helping this mission because during solar minimum, things are simple. There aren't very many sunspots. There aren't very many of these solar storms. What ones we're seeing are small, and that allows us to individually identify every single event.
And then later, as Parker continues to observe the sun, we'll see this ramp up of activity and energy bursts, and we'll be able to see the more complex and bigger energy bursts.
In the coming years, the probes will witness up close the power of the sun during its more active phase, as it spirals closer and faster to the star.
Parker Solar Probe is already the fastest human-made object. As it gets closer to the sun and spirals in and goes faster and faster, it will reach 500,000 miles an hour. So we are so excited to see the results as Parker continues on its mission.
Before Parker Solar Probe passed through the sun's Alphen boundary, it detected kinks in the solar wind, where it would momentarily double back on itself. Scientists call them solar wind switchbacks, but had no idea of the mechanism that caused them to form. As Parker got closer and closer to the sun, it detected more and more of these switchbacks. It was able to track one of them to its origin on the visible surface of the sun. On the surface, you can see defined cells as heat rose from beneath. These convection cells churned and created funnels of magnetic energy above the surface. Scientists concluded that these switchbacks form inside these funnels before rising into the corona and beyond. This is only one piece of the puzzle. However, scientists still don't yet know how they form. Over the next few years, Parker will keep looking for clues as it explores our sun up close. The sun is the only star we can study like this. It is also the only star we know that supports life on at least one of its orbiting planets. Understanding it is critical as we search for life beyond our solar system.
That will link directly into the question, are we alone in this universe? And that is one of the biggest questions for humanity to answer.